So already 30, 31, 30 people have joined. Yes. Kannaki, hello. You please give me the attendance after the class. So I straightway go to share this file. Control PowerPoint. So we were here, right? In the last class. Okay, so we were here. So what was that? The problem that we have faced is that when we have seen the product, these electrocyclic reactions are very much stereoselective and also stereospecific. But it depends on, that means it will give, the product will be dependent on also on the geometry of the reactant, and the product formed will depend on whether the reaction is carried out under thermal condition or photochemical condition, and also on the number of the pi bond. So we'll understand this once we take the theory. But before we go to theory, we have to really understand the concept of a very preliminary. If we have the preliminary idea of molecular orbital theory of pi bonded system, that is sufficient for our purpose. So I'll be taking today will be dedicated to that part, that is understanding these molecular orbitals of different molecules having pi bonds. So theory will be FMO theory, that means frontier molecular orbital theory. That is the theory. And this theory was being given by Woodward and Hoffman. So once we have this, but before we have the theory, we have to understand about the molecular orbitals of molecular orbital theory. That means this concept of linear combination, which is formed by the linear combination of atomic orbitals. Are you getting my voice, all of you?
Yes, sir.
Okay.
Yes, sir.
So I think we start with which is the simplest molecule? Tell me. Simplest
Hydrogen.
molecule. It is hydrogen. So we start with hydrogen. So what is their hydrogen? Hydrogen bond is hydrogen molecule is formed by the combination two atoms of hydrogen, and the atom of hydrogen is having its electron, one electron which is present in one s1. So that is the electron where this which is present in hydrogen atom. So when a molecule is formed, it is, so what we'll be doing, here, we'll be understanding about the hydrogen molecule. Then we go to carbon-carbon sigma bond. Then we go to carbon-carbon double bond, which is having one sigma bond and one pi bond. And then we'll be interested to know about the conjugated pi bond system. So that is what is. And also we'll understand what is homo and what is lumo. What these two words means? Can anybody expand this homo and lumo?
Highest occupied molecular orbital.
Highest occupied molecular orbital, and LUMO stands for
Highest
unoccupied molecular orbital. So these things we have to understand this. Many of you know this, But we have to, once we take this reaction, we have to understand this one thoroughly. So the first molecule will be hydrogen. So how this hydrogen molecule, so this is what hydrogen molecule, molecular orbitals which are formed. How it is formed, that is this is when two atoms of hydrogen combines, which has got an energy, by this side we have got this energy, picture of that energy, increasing energy in this. So suppose the atomic energy of, atomic energy of this atomic orbital of hydrogen is at this level. When the molecule is formed, two atoms of any, now how a bond is formed? Because hydrogen molecule has got one bond, which is there. It's disturbing my screen, actually. I don't know how to bring it on the top. Anyway, uh, hydrogen molecule, when it is formed, hydrogen molecule is formed by the combination of two atoms of hydrogen, which has got a sigma bond. And when the bond is formed, one atom of hydrogen combines with another atom of hydrogen, giving rise to two molecular orbital. One atomic orbital, which is 1s1, another atomic orbital which is combining to having this another 1s1. So it is atomic orbital combining to give us molecular orbital, not the electrons are combining. Don't I think some of you may have that concept that electrons are combining. It is not electrons which are combining, it is the orbitals, atomic orbitals are combining. So one atomic orbital, two atomic orbital combined will give rise to two molecular orbital. But in terms of energy, one orbital will have lower energy, so its energy comes down, and another will have higher energy. That energy goes up. After these orbitals are formed, so this becomes the two molecular orbital of hydrogen. Now, after the orbitals are formed, now electron will occupy these orbitals. And occupation of electrons will follow all the rules that is governed in the filling up of the electrons in atoms. So first will be Auber principle, the lowest energy orbital will be filled up first. So that way this becomes the lower, this becomes lower. So it is coming here. And the electron, both this electron will be here. And this electron remains unoccupied. And because the type of bond is sigma, we call it this sigma bond. And this one is termed as a sigma star bond. But these are just notations which are used. This is bonding orbital, and this is what is called anti-bonding orbital. ABO means anti-bonding orbital. So that is the situation in case of hydrogen. Now let us extend this one to a molecule with carbon-carbon sigma bond. A carbon-carbon sigma bond. How this carbon-carbon sigma bond is formed? The bottom we have this carbon-carbon sigma bond. That is, this is one carbon, this is another carbon. They are formed by the overlap of sp3 orbital of one carbon, isn't it? sp3 orbital of one carbon with the sp3 orbital of another carbon. Now, sp3 orbital is just like an atomic orbital, but only thing is that it is an hybrid orbital. It is not a pure orbital. All right. So here also two orbitals are combining, one orbital from this carbon, another orbital from this carbon. They are combining to give us two molecular orbitals. And there, one of them energy will come down. One of them, the energy will come down. So it has come down this much. Another orbital will equally go up. So it has gone there. So we show it by a line here, just by a line. This line is shown. And the other one is also by a line. Just this line is here. So, and like hydrogen, so in the two electrons are there. One sp3 orbital has got one electron, another sp3 has got another electron. So both of them will come, will have two electrons. So now this time in the molecular orbital, both this will go and occupy the sigma orbital, bonding orbital. And this one will remain vacant. Now, in terms of orbital, how this bond is formed? By overlap of orbitals. But if you see this p orbital, sorry, this sp3 orbital, how does it look? We have got a small lobe here, and a big lobe on this side, right? And this phase of this is the phase of this, and the other one is having just the opposite phase. We'll just talk a little bit about that phase and the wave function and all these things in our next slide, maybe. So what we'll be having, so this, and there is a node here. Node is the transformation of phase where it takes place. So that is the node at the middle. Overlap will take place only when the same phase come together. So in the bottom, you find that this phase and this phase having the same phase, similar phase, they will overlap. But when you go to the other one, this one on the top, this is one phase, but this is coming with another phase, opposite phase. So when two dissimilar phases come together, there will not be any bonding. So this becomes what is we call, this is a high energy molecular orbital. In other words, we call it anti-bonding orbital because there is no electron under normal condition here. And it is given the symbol sigma star. So that is how we represent this. We represent this this carbon-carbon sigma bond. Got it? Hello? Respond.
Yes,
Yes, sir.
Okay.
yes, sir.
Now we go to next one. These are two division line between these two. Now wave function. Let us have some about what are these orbitals. These orbitals, atomic orbital or the molecular orbital, these are nothing but some wave functions. I am not an expert in this field and I cannot give you one, but you have studied this one. Now, if we imagine a wave, suppose we have a wave in a box that you have concept you have taken. And you have got one string here, and another string here. These are being connected by a rope. So this rope may be, one wave may be formed here like this. I'm showing you the picture. Let me show the picture directly. Ah. So this, particularly in a box, we have studied that one, right? It forms a wave. So now here, these are the different stage of the wave. So first, the lowest one, you find that the wave is just one phase that we are seeing. It comes like this. Next, it goes, it may come like this next higher one. It goes here, then comes here and forms another wave. Next one, you find it is going like this. Next one like this, and it can keep on increasing like this. Now, if you analyze their energy and function and their different, so what we see, here this, as we say, first one, the lowest one, this wave is only in one phase, one phase. That this is a phase, not, okay. This is, the whole wave is in one side of this. So it has got one phase. But when we come here, the next one, we have, it is having two different phases. Sometimes this is called, if it is termed as positive, this is negative, but don't consider that this is a positive sign and negative sign. Two different phases. So one phase, this is the opposite phase. And where this phase changeover take place, this point, middle point, that is called a node. This is called a node. So here only one phase. Here we have got two phase with one node. Here we have got uh, three phases. This is one phase, then opposite phase, then this one again, same phase as this one and this one, same phase. But this is opposite phase. They will not mix up actually. Same phase can mix up, opposite phase cannot mix up. They cannot mix up and add together or subtract, so that cannot happen. Opposite phase, rather subtraction take place. Same phase, you can add the phase, add the wave character and get a bigger wave and all these things. I think you have. And if you go to the next higher one, you have got one phase, two phases on one side and another opposite phase on the other side. And with how many nodes? How many nodes are there? One node, two node, three node. We have got three nodes. And here, if we see, the energy and the node have direct connection. Higher the number of nodes in the wave function, in the wave, rather it is not wave actually, wave function, higher will be the energy. So that is what, one way you can accept this one. I think you have got this idea, yes or no? Tell me. This idea,
Yes, sir.
you have got some idea about physical chemistry. This is what you study this. We'll be just using a very preliminary concept of that one here. You got it or not? Huh? You know it, no? Hello?
Yes.
Yes.
Yes, sir.
Okay. Now, our orbitals are also nothing but wave functions. So let us see it in terms of our orbitals here. So what is this one? So our p orbital, right? This p orbital with, now what is this? We see this is one lobe. It has got one lobe and this lobe. These two are opposite phase. They are not of the same phase. So, and also drawn by a color. This is shaded and this is completely shaded. This is no shade is there. And this is what is a node. You see here, this point is a node. And if you take a hybrid orbital, suppose hybrid orbital, sp3 orbital or sp, all hybrid orbitals have got this shape. So this phase and this phase, they have got they are opposite character, opposite phase. And this becomes the node. The middle point is the node. That way. So this is, with this idea, let us go further. Let us go ahead and see what we can, what we see in the next one. All right, so we come to the simple part. Now what we'll be doing, we have taken the sigma bond hydrogen molecule and carbon-carbon single bond. Now we'll concentrate only on pi bond, not others, because our pericyclic reactions, pericyclic reaction we have got, it is only mostly the pi electrons which are involved. So we start with carbon-carbon double bond. When we say carbon-carbon double bond has got two bonds. One is sigma bond, another one is pi bond. So sigma bond we are not taking. We are taking only the concept of pi bond. How this pi bond is formed? It is by the combination of these two atomic orbitals, p orbital, rather p1 of this from one carbon and p1 from another carbon. So they combine to give us two molecular orbitals. One will be having lower energy, one will be having lower energy, and another one is having higher energy. And because the bond is, the type of bond is pi, so we call it, this is pi, and the other one is pi star. All right. And in terms of wave function, now how this pi will look, the bonding orbital will look. Now these two carbon atoms which are there, these two p orbitals, the two p orbitals which will be there. Now the same phase will come together. So there will be a bonding situation. Here also bonding, here also bonding, because this is also, you see, not that they are opposite means, but opposite of the same opposite character. So they will form the bond here. So that is what is your bonding to your pi orbital. And the other one will have a node. This one is having a node here. Once the node is here, so here without any node, this one is without any node, and this one is with a node. So as the node comes, this phase changes like your wave phase. So this blue phase here will meet the white phase. So there will not be any bonding here possible. So here also no bonding. So that is what is, we call it anti-bonding. But remember, now this bonding and anti-bonding term will not be very suitable here. These are some wave function. We can call it as pi1 and pi2. Even I can call it, instead of telling it pi, I can call it pi1. And this one as the pi2. We should not use the term star also, because we'll be having more number of them. So pi star is not a term that should be used now at this stage. So pi1 and pi2. Also, we can use the notation like psi. So this becomes psi1, this becomes psi2. Only the difference is that this is of lower energy, this is of the higher energy. And in the ground state, these electrons which are there, two electrons, one electron coming from here, one electron coming from here, both these electrons will be present here. I think it is clear. Okay.
Yes, sir.
This can be represented. Now I am giving another picture here with some complete situation, like a carbon-carbon. Suppose we have got a molecule with carbon-carbon single bond, which is there. So in a carbon-carbon single bond, what is there? Only sigma bond is there. So we'll be having sigma and sigma star. So only this. And the electrons will be present here. Electron will be present here. And this upper sigma star is vacant. This arrow up I'll just show, and this energy is shown here. This energy which is there, energy is shown here. This energy is as if we go up. In carbon-carbon double bond here, carbon-carbon double bond, what is there? We have got one sigma bond and one pi bond. One sigma bond and one pi bond. So sigma bond was formed first. So this electrons is here. This two is sigma from sigma bond. But for pi bond energy is higher than the sigma bond. That means it is less stable. So higher energy. So its energy is little higher. So its electron will be here, and this pi star which will be there as the pi star. This pi star which is here I have written. So that is. But we have also sigma star. So in case of ethylene, this is the molecular orbital that is here. The picture is here. This is all right. So we have got four orbitals. One is your sigma, sigma star, pi, and pi star. Now, when there are four, the electrons are there, their energy levels are different. And if we see this, these electrons which are there, just see the electrons which are there. Here you see this. This is the one which is present at the highest occupied. So we call it HOMO. This orbital is HOMO. And unoccupied orbital, we have got how many unoccupied? This is unoccupied. This is this is unoccupied, and this is also unoccupied. But among the unoccupied orbitals, it is the lowest energy one is more important. So this becomes your lowest unoccupied molecular orbital. And here you see, suppose under photochemical, we can, if we want to promote one electron from the sigma bond to the other bond, so you just see, it's very high amount of energy you require. Very high amount of the promotion requires this, it has to go up like this. But from here to here, from pi to pi star, we require a less because promotion will take place from highest occupied to the lowest occupied. Now, in this case, in case of carbon-carbon single bond only, what was the homo? Homo was sigma. This is homo, and this becomes lumo. And that takes quite high amount of energy. And this energy of absorption, that means the electronic promotion will take place between sigma and sigma star and requires very high energy. The wavelength of that energy, that will be required is 150 nanometer. 150 nanometer wavelength. And energy and wavelength are inversely proportional, yes or no? Energy and wavelength are inversely proportional. So this is shorter wavelength than this one here. Sorry, here we require pi to pi star. You see here, the energy gap is less here. Energy gap is less, this much energy. But here we require more. So it is 170 nanometer. There it is there it is less than that. Sorry, more than that. So it is wavelength of absorption is higher, wavelength of absorption is lower. Oh my goodness. Okay. So we go to the next slide. Now, pi molecular orbitals of conjugated system. We have just now what we have seen the simple system, right? Now we are going to conjugated system. Pi molecular orbital of conjugated polyene. So which will be the simplest polyene? Tell me, conjugated polyene. Simplest? Tell me. Huh? Conjugated polyene. Which is the simplest?
Diene, sir.
Huh?
Diene.
But diene, which one? Huh?
Butadiene.
It is 1,3-butadiene. You cannot say that only butadiene, maybe also 1,2-butadiene also, which is will be allele. That is. So it is 1,3-butadiene. Yes, that is the conjugated diene. Now, so here. So it is conjugated diene, that is there. Now, in conjugated diene, what is the system? Let us see. So this is a conjugated diene. Just see. You see here. This is double bond, then single bond, then double bond. So that becomes conjugated diene. Now we are not considering sigma bonds. The sigma bond is there, the pi bond is there. We are not considering sigma bond. Only we are considering pi bond. So what will be there? We have got one p orbital in this carbon, another p orbital in this carbon, another p orbital here, another p orbital. So we have got total number of 4 p atomic orbitals will be there. And so that 4, because what is linear combination of atomic orbital? The number of atomic orbital to give you molecular orbital. Atomic orbitals combine to give us equivalent number of molecular orbital. So if 2 of them combine, we get 2 molecular. 2 atomic orbital combined, we get 2 molecular orbital. 4 atomic orbital combined, we get 4 molecular orbital. Like in hydrogen, 2 atomic orbital, 1s, 1s, S1, 1s and 1s. So 2 atomic orbital combined to give us 2 molecular orbital. One was sigma bonding and sigma anti bonding. So was also in the pi bond. 2 at p orbital combined to give us 2. It has already giving the signal. 10 minutes more. So we have to wind up with this within this 10 minutes. It combines to give us 2 molecular orbital. So here we have got 4 atomic orbital, p orbital. So it will give rise to 4 pi molecular orbitals. So let us see how it happens. This may be considered, you see here, the next line is written, may be considered to be formed by linear combination of pi molecular orbitals of 2 C double bond C. Just see here. This 4 pi molecular orbital coming from here. As if we have added, like two atomic orbital give you two molecular orbital, but here we can consider it to be addition of one C double bond C and another C double bond C. But every C double bond C, what was there? Pi and pi star, pi star. From here also we have got one pi and another pi star. Now, when the molecular orbital is formed, the molecular orbital forms. So this molecular, this one, this orbital and this orbital to be first combined, because the combination has to take place with comparable energy. This one cannot combine with this one because they are too far away in terms of energy. So this one will combine with this one of another. So how many? This pi 1 and this is pi 1 plus 1 will give another 2. But in terms of energy, this energy will come down, for another energy will go up. And similarly, this one will combine with this one, giving rise to two, again, molecular orbital. One will be here with this energy, another will be this energy. Now I am not giving the term pi and pi star and all these things. Now we'll be shifting to the term psi. Also we can call it pi, doesn't matter. So we have got now total number of four pi molecular orbitals, 4 pi molecular orbital. This termed as one is this is psi 1, then psi 2, psi 3, psi 4. So this 4 pi molecular orbital in the conjugated butadiene, conjugated 1,3-butadiene will be psi 1, psi 2, psi 3, psi 4. And now electron will be occupied according to upper principle. The lowest energy will, so lowest orbital will go here, get, first 2 electrons, next one will have 2 electrons. Psi 2 will have 2 electrons. And psi 3 and psi 4 will not have any electron. Now in the process, what has happened? What has happened? We'll be having this becomes your HOMO, and this becomes psi 2 becomes HOMO, and psi 3 becomes LUMO. Now, if you have to excite this molecule, so how much of energy you require? You require only this much of energy. An electron has to go from psi 2 to psi 3. But in case of one ethylene, how much energy was this much? This much of energy. But this time in butadiene, how much is energy? Energy required is less, this much, because of this combination. So, so for the promotion of electron, we require less energy, and less energy means in terms of wavelength, it becomes higher wavelength. So you find here the pi star transition requires 214 nanometer, 214 nanometer. That means longer wavelength. So this also is important. Longer wavelength. That is telling about that we are having this so many. So now let us see it in terms of, because we have seen last time also in terms of pi molecular orbital, how it looks. This is how it looks. These are this psi 1, psi 2, psi 3, psi 4, what they are? They are nothing but wave functions. The psi 1 will have no node. Psi 1 will have no node. It is here. So all the p orbital here will be of the same phase. Psi 2 will have one node. So that middle you find this broken line. This is your node. So then psi 3 will have two nodes. As we are increasing the energy is increasing, the number of nodes also will increase. And psi 4 will have 3 nodes. 1, 2, 3. And with this point, as the node comes, as the node comes, this phase will change. So this was blue and blue, but from here it will become, this will become white. That means opposite phase. And here there is no node, so this one also has to be opposite phase. And this one, so psi3 will be having this. So in terms of wave function, this is how it will look in terms of orbitals. You got, this is very, very important for our pericyclic reaction. Is there any problem in understanding this, how we have got these nodes and the phases? Yes, hello. And it is very simple. First one will have no node, second one will have one node, then two node, then three node. As the node comes, you just shade this shade of the p orbital will change. In some book you may find here this one is given positive sign, another one is given negative sign. But once you give positive and negative, many will think that in terms of charge. It is not charge, it's the phase. It is the phase of the wave. Hello. Have you understood this? Because once if you don't understand
Yes, sir.
this one, we cannot go.
Yes.
So this is with the butadiene, all right? And it is very simple. I'll be forwarding this note also to you. Now if I go to conjugated triene, so what will be triene? Very similar way. We have to take this one, a very similar way. Oh, we are just having 2 minutes left. We have 2 minutes left. So what will happen here? We are just, see here. So 1, 2, 3, 4, 5, 6. So there will be 6 p orbital will give 6 pi orbital. How it will look? Just see. So it is psi1, psi1, psi2, psi3, psi4, psi5, psi6. And how this one? You see pi to pi star transition at the bottom. Just see at the bottom, pi to pi star transition requires less amount of energy, because as the conjugation increases, the transition between HOMO and LUMO, they come closer. So that this transition requires less and less energy. And this is also spectroscopy. You have studied this, yes or no? UV visible spectroscopy. Hello, tell me. We are left with only 1 minute 2 seconds. Okay, and this will look like this, and very simple here. First one, no node, then one node, two node, three node, four node, five node. And with every node, there will be. So psi1, psi2, psi3, psi4, psi5, psi6. I think you can draw it very easily. And with the change of the node, this phase will keep on changing. Yes? All right? Hello?
Sir.
So I think now you write down yourself.
Sir.
Yes, you write down yourself. I am just stopping this share. Because just 1 minute less than 1 minute left, and I'll end this and you rejoin again.